And I've learned a lot during this project from working with Dinesh and the group lead at Berkeley, Sergey Levin. Dinesh nowadays is at University of Washington, but then was a postdoc in Sergey's group. So imitation learning is I hope my videos come through, is a powerful method to learn complex behavior. It's used in practice to solve complicated problems, such as driving cars, flying drones, grasping fish. And the simplest form of imitation learning is called behavioral cloning, and it uses a data set of expert demonstrations. Let me try to get a pointer. Expert demonstrations, map them to expert actions using some learned models, such as a neural network. And even though it's very practical, it is not quite perfect. And one of the reasons why it is sort of fundamentally flawed is because when we have the expert in some state in the world and a cloned imitator that's trained through imitation learning, and we run these in the environment, then we see that small errors in the imitator that are inevitable, they accumulate and may bring the imitator to realms of the state space that are not covered by the demonstration data set. So we have a shift in the distribution of state. This is a very generally known problem, for example, mentioned in the work of Ross et al. In Dagger. And there they show a general solution to this problem. But in this work, we look at distributional shift that arises due to causality and see if we can find better solutions to this kind of distributional shift that is due to causality compared to the general Dagger solution. So consider, to sketch this, this problem, the causally caused distributional shift, consider this hypothetical motivating example. And we ask the question, does more information available to the learner always improve its performance? Well, in supervised learning, this is generally the case, but what happens in imitation learning on a distributional shift? So in this hypothetical example, we learn to drive a car, and we imagine two scenarios. In scenario A, the learner has access to both the windshield that contains the situation on the road, as well as an indicator on the dashboard. And this indicator on the dashboard that blinks whenever we are braking. And in scenario B, the input is just the road and the dashboard is blacked out. Now what we do, we train an imitator on the data of both these scenarios, and we run these in the world. So the imitator gets good imitation losses when we run them on the demonstration data set. But when we run them on the road, we see the following. We see that in scenario B, the imitator correctly learned to focus on the person on the road and hence brakes whenever a person appears. But what the imitator in scenario A does is it learned to focus on the brake light and brakes whenever the brake indicator is on, and thus fail to brake if there is a person in front of the car, but the brake light is off. So what happened is that the imitator learned to focus on the facts of the expert's behavior rather than the causes. And this leads to the surprising result that we have more information available to the learner, but this leads to worse generalization when we execute the imitator on the road. We see this as a symptom of what we dubbed causal confusion, in which cloned policies fail to generalize because there is an implicit underlying causal model of the expert's behavior that was wrong. So what happened here? Simplified, we can imagine this as two random variables in this state. One is the road view and the other is the brake indicator. And we know that, and we're trying to predict the expert's next action. We know that the expert only cares about the road view and would ignore the brake indicator. And we would call this a nuisance indicator, a nuisance variable. However, there's a past state in action that operates as a confounder, and this makes the brake indicator and the expert's next action still correlated, even though it is not a direct cause. So if we now learn an imitator, we can learn an imitator that, as the expert does, just focuses on the road view, or we can learn an imitator that wrongly assumes that both variables are causes. And this leads to the erroneous effect that I described before. So in general, if we assume that we can factorize our state into n such variables, we can imagine 2 to the n possible imitators, each of which treats a different subset of state variables as causals. And only one of these corresponds to what the expert does, the causal model of the expert. And the goal is then to find out which of these causal models corresponds to the experts and hence has the best performance. So in the rest of the talk, I will first go through the prior example in a quantitative way, so you can see this effect popping up in a very simple case. Then I show that this phenomenon also exists in slightly more real setups in simulation, and describe how we evaluate the success of our setup. Then I will go through a couple of solution strategies we propose and discuss the results. So first, let's look at a very simple analytical example. We have the following market decision process, and we cut the state again into person on the road, a binary variable, the brake light being on. The action variable is whether we brake, and we have a reward. And here we say that a person stays on the road most of the time, so appears or disappears with a probability of 100. We furthermore say that if we brake, then at the next time the brake light indicator is on, and the expert only considers whether the person is in front of the car, because the expert will behave optimally, namely to brake whenever, if and only if, a person is on the road. And we incur a strong negative reward if we do not brake, but there is a person on the road. So to give a sample trajectory of an expert, for some time there's no person on the road, then a person appears, the expert brakes, and the next time step the brake light goes on. This continues for some time steps until the person disappears, the expert stops braking, and the next time step the brake light goes off. So this is optimal behavior. So now we can try to model the policy space, and here we make a simplifying assumption such that we can show the policies in 2 dimensions. Namely, what we do is we assume basically a naive Bayes assumption that we let our policy be dependent on whether there is a person in front of the car and whether the brake light is on. And we parameterize it with 2 parameters. So with 2 parameters, we describe the whole policy space. The expert here corresponds to infinity for alpha and 0 for beta, meaning that the expert would brake if and only if P is true or a person is in front of the car. So now we can ask of all these policies in this 2-dimensional space, do they agree with the expert on demonstration data? Second question is, do they take the same action as when we run the imitator? Do the expert's decision and the imitator's decision agree? And the last question is, does the imitator attain high reward? And here's a bit of a complicated plot. It tries to answer all these 3 questions for all the policies in this 2-dimensional space. So in the x-axis, we show the alpha parameter for the policy. And in the y-axis, we show the beta parameter for the policy. So each point in this xy plot corresponds to 1 imitator. Again, the expert has infinity for the p parameter and 0 for the l parameter. What we would see is that here in the right middle side, the imitator is similar to the expert. It achieves the optimal reward of 0 and gets a very high accuracy both on rollouts as well as on demonstrations. However, if we here look on the top left, we see that there is an imitator that achieves around a 90% accuracy on demonstrations, but at the same time a very low accuracy on rollouts and close to the most negative possible rewards. And that is because this expert, this imitator here on the top left of this policy plot, has a very high L parameter, so it focuses a lot of its attention on whether the brake light is on. And we see that this imitator agrees well with the expert on demonstrations, but it performs dramatically when it is executed in the world. And we say that this this imitator is causally confused. So what do we mean by that in terms of these graphical models? Well, again, if we say that the state can be partitioned into these discrete many state variables, that and each of these state variables can be an arrow to the next expert's action, and an imitator is causally confused when it treats a wrong subset of these state variables as causes to the expert's behavior. So how do we go about demonstrating this in slightly more, demonstrate this phenomenon in slightly more real scenarios? By the way, I should ask, say if there's any questions, I'd be very happy to make it more interactive and answer any questions that arise on the go. So maybe I'll ask now, are there any questions pertaining to the previous section? Well, all right, then I go on. Let's try to demonstrate this in more realistic scenarios. So this is prior work of Wang et al. Also from Berkeley. And they learned an imitator to drive in the simulator Grand Theft Auto 5. And they treated two imitators, one that had access to a history and one that did not have access to a history. And what it means is basically that we, whether the no history has as state variables just the present state, and the history has additional to that concatenated prior states and actions that the imitator encountered. And we could think of this as similar to the brake light example, because the current state is more of a cause of the expert behavior than prior states are. And whenever we from the history could infer prior actions, or if the prior actions are explicitly encoded in the history, then the imitator could implicitly learn to focus on these nuisance variables in the history and perform poorly. And this is exactly what we see. When we look at an imitator that has, when we look at the held out demonstration error, so how well does the imitator agree with experts on states that have been encountered by the expert, we see that that adding history improves the model. But when we, so here, the label here should be errors during driving. Then we see that adding history increases the number of errors it makes during driving. So here we see a similar phenomenon, a similar symptom of causal confusion as before, namely that adding more information to this learner makes it perform well during demonstrations, but makes it generalize worse when executed in the real world. And other works found similar phenomena. So how are we going about to simulate this? So what we do is we take a couple of standard control experiment benchmarks and start with the original state of the simulator that we assume contains only causal variables, and we add to this state some variables that are not causal, that are nuisance variables, to create a confounded state. And what we do is we simply concatenate the past action, again corresponding to the brake light indicator that were representative of the past action. So then we compare the performance during training as well as during execution in the real world of this original state versus the confounded state, and see what the rewards are. So to compare, scenario B that had the brake light indicator blacked out corresponded to the original state, and scenario A, which has this brake indicator, corresponds to the confounded state in which the past action is concatenated to the state. So the benchmarks we look at, which we do this for very simple ones, mountain car and Mujoko hopper. The first one is a discrete action space, and the second one is a continuous problem with continuous actions. And we also look at the 3 games in the Atari simulator, Pong, Enduro, and Up and Down. And here we again want to add to the state some news and some confusing information regarding previous actions. And what we do is we want to stay within the visual realm by making all inputs to the learner visual. Is we draw as a nuisance variable the past action that was executed in the simulator as a frame on the draw it as a digit, as pixels on the frame of the simulator. And this again has the potential confusing effect because an imitator could learn to look at these digits and try to infer past actions from these and try to predict future actions in a non-causal way. But for our solution strategies, as I said before, we would like to partition the state into state variables, a subset of which is causal, and the other subset is non-causal or nuisance variables and should be ignored. Pixels are generally a poor causal variable. It's weird to talk about the causes and the effects of pixels. So we would like to have some disentangled representation of state on top of which we can reason causally. And it's a hard problem. And what we do in this project is to simply use a VE encoder that is trained on rollouts from the simulator, create a representation of the frame through just encoding by the VAE, and then treating the individual dimensions of this encoding as potential random variables. And there are certain problems with this approach, which I'll go into in the end, but it at least gives us some way of having a small set of variables about which we can attempt to reason causally. Oh, and we used 30 to 50 dimensions, by the way, for the VE encoding. So now we train an imitator on the original state that does not have anything added to it, as well as on the confounded state, which has this nuisance information added. And we plot reward attained by the imitator. And on the x-axis, we show how many demonstrations were used to train the imitator. Because we expect that with a small number of demonstrations, the suffering from distributional shift is worse compared to if we had basically infinite samples and complete coverage of the state space. So in all cases, we see that the original imitator gets close to expert rewards with a relatively small number of time steps, whereas the confounded imitator that has access to more information performs significantly worse for the same number of training samples. So here we see that also in these cases, causal confusion is present. So how might we go about solving this? So one thing you could imagine, and especially coming from the causal literature, this is a very standard way to do, is just to test conditional independence. Basically, what you could do is, if you test whether the variable x2 is conditionally independent with the action, given the other state variables, if this independence holds, then it's not a cause. If it does not hold, this arrow exists and x2 is a cause. And this is a standard assumption, but this assumption has a critical, this test has a critical assumption, namely faithfulness, meaning that all the conditional independence relationships that are present in the model of the expert, in the distribution of the environment and the expert combined, are also present in this graph. And importantly, in deterministic environments, this faithfulness assumption does not hold. Because, for example, here, if x2 is a deterministic function of the prior state in action, then if we were to Oh, I made an error. So the test that we would like to do is test whether x2 is independent of a2 conditional on the entire past. Because in this Markov decision process, all arrows always point in the future. So if this conditional independence test holds, then x2 is not a cause of a. If the independence test does not hold, x2 is a cause of a. But if we see that x2 is an deterministic function of the past, then this independence does always hold, even if the arrow is there. And this is because this faithfulness assumption is violated, which is the case when we have some deterministic element in our environment. And we often do in scenarios that we care about. Not all the state needs to be deterministic, but when some aspects are, such a test no longer works. Here I have some numbers to indicate that indeed this conditional independence test does not work in the mountain car case. So instead, what we do is the following. What we would like to have is two things. One is the causal graph of the expert, basically the knowing which subset of variables is a cause to the expert. And secondly is a neural net, that's what we choose, predictor to predict the expert's action given the causes. The first step is the hard step, because once we have solved the first step, we can just use standard behavioral cloning to do the second. So what we do is we first learn a graph parameterized policy. This means that we try to learn one single neural network such that if we feed it a graph, for example, this graph in which the first and the fourth variables are causes and the other two are not, it gives us a trained close to optimal policy. And in the second, we have this whole set of policies that we learned, and now we are going to do intervention to try to find the true graph amongst these. So what we do is we parameterize our graphs in the simple case as a binary vector, where 1 indicates a variable is a cause and a 0 indicates that a variable is a nuisance variable. So we map our problem in this specific case from the problem of these causal graphs to the problem of finding the right binary vector. So in the first phase, we're going to try to learn an optimal policy for each possible causal graph. We could learn 2 to the n possible graphs, but for obvious reasons, that's impractical. So we parameterize this with a single neural network. For training, we do the following. We sample a random graph. Then we take our state from our behavioral cloning demonstration sample. And then we mask out all the parts of the state that, according to the graph, correspond to a nuisance variable. We transform this with a neural network into an action prediction, which we train with behavioral cloning. So we train all these 2 to the n graphs jointly through a single neural network. So that's the first phase. And in the second phase, we'd like to infer the right causal graph. From these prior arguments about faithfulness, we can't just simply do a simple independence test. And the expert demonstrations are themselves are insufficient to figure out which graph really corresponds to the expert. And we need to actively intervene in the states to reach new states that the expert has not reached, and so that we are able to evaluate the causal hypotheses. So what we do is we intervene by executing some of these policies. So rather than using the expert, we use one of our trained policies corresponding to some causal graph to collect new states. And then based on these states, we can score the graph and pick the graph with the highest score, which we then say is the optimal graph. We do 2 ways of scoring these. One is we we find these new states, then we query the expert on what it would do on these states and find the graph that is most in correspondence with these experts. And in the second, we do something similar, but using rewards. I'll go into that in a bit. So we would like to intervene to explore new areas of the state space that are not present in the demonstration data set. And what one would maybe like to do ideally in the simplest case is just to modify some state variables such that we are in regions of the state space that are not in the demonstration data set, and then ask the expert, what would you do? But generally, we're not really in sort of practical setups really able to just arbitrarily modify the state. So what we do instead is we know that this is a sequential decision problem. So when we alter prior actions, we know that consequently the state distribution changes. So here we have an example of a generalized interventional state in which we can modify the state distribution without actually changing it by just picking different actions than the expert would take. So once we have collected these new states, what do we do? So in the first mode, we are going to intervene using expert queries. So we collect some trajectories using these policies, and then we find the states in which the graphs have most disagreement. We do this by a query by committee active learning strategy. Then on these states, we query the expert for its label, what would it do? And then we pick the graph that is most in agreement with the expert and select this as the optimal graph, the output of our algorithm. Alternatively, in the second mode, what we do is we assume that we can execute in the environment and collect some rewards, but only a small number of such rewards. So what we do is we initialize a distribution of our graphs. We pick a graph from that distribution, execute the corresponding policy in the environment, collect a reward. By doing so, build a data set. And then we update the distribution such that graphs that whose policies attained high rewards become more likely, and then we repeat. We do this a couple of times, and then pick the mode of the distribution as the output of our algorithm. So in the amount to car and hopper setting, we here have results where we scored the rewards based on expert queries. And we see the upper bound of performance here is how the imitator behaved when it did not see all this confusing information. The lower bound is the performance that the imitator reached with the confusing information, with the confounded state. And what we do is we run our algorithm on the confounded state, and we see that after a relatively small number of queries to the expert and the running of our algorithm picks the graph whose policy achieves a reward that is much more close to the original, much improved reward over the confounded, getting close to the performance of the original imitator. In comparison, the Dagger baseline, where we just run Dagger and after a similar number of queries to the expert performs significantly worse. We have plots in our paper that show that you need orders of magnitude more expert labels provided through the learner by Dagger to achieve similar performance as our learner does, that is sort of has more this causal structure baked in. Similarly, when we on the Atari games, we score the potential causal hypotheses using the rewards that it gets after a limited number of runs in the environment. So in the x-axis, we have the number of episodes we use to score our graphs, and in the y-axis, the reward. And again, we see that our model gets close to original performance and much improves over the confounded start. As a baseline, we have what is proposed by Banzo et al. In 2019, which is to basically train using dropout. So on the features that you suspect are nuisance variables, you apply dropout during training, and then during execution, as you do with dropout, you never mask it. And we see that this only improves performance in a limited number of settings and underperforms our strategy. So, these are the two main solution strategies. As a third side, we explored with causal discovery. Causal discovery is where you try to infer some information about the causal structure passively, so prior to without any intervention. And we use this by first inferring some belief passively from the expert demonstration data set, and then use this belief as a prior to the previously mentioned interventional methods. So what you do in Bayesian causal discovery is basically just finding the posterior over graphs and parameters over parameters of your model, such that graphs and parameters that explain your data well are more likely in this posterior. And as often this is an intractable problem because it's combinatorially large in the number of graphs and very large in the number of parameters. So a classic trick is to try to apply variational inference to make this problem tractable. So what we're trying to do is find some belief over graphs and parameters, such that, again, this belief is high for graphs that explain the data well. In particular, we look at a variational family in which we model some correlated, you can see again G as these binary strings. So we want this to be a distribution over binary strings. For the parameters of our model, we're not Bayesian because that was too complicated. So basically what we model as a variational family is some correlated distribution in the space of binary strings. And then we have a variational objective, which I'll skip over now, where we use some bounds to come up with a tractable optimization objective, such that we can try to infer some belief over graphs. And for training, what we do is basically we sample a multivariate Gaussian, which we transform to a distribution over graphs. And then we use the graph again to predict the action. And then by doing so, we learn the parameters of this variational distribution such that graphs that predict the action well become more likely. For optimizing the objective, we then also predict the multivariate Gaussian from the graph we predicted, but that is just to get an estimate on the KL divergence necessary for doing the variational inference. So we have some results of this procedure in the paper, and basically the consequence is it doesn't work. The conclusion is it doesn't work very well. Reason for which is that it worked reasonably well for the 3-variate mountain car scenario, but whenever the number of variables becomes larger, the procedure fails for various reasons that we can go into in the end. So here are some visual results that we did from the simpler method without the variational causal discovery, scoring the hypotheses using the rewards, by executing them in the environment and collecting rewards. So what we started out with is the imitator on the confounded setting, where the digit again indicates the expert that the action that the expert has priorly taken. And we see that this agent mostly loses from the opponent. The opponent here is the AI that's part of the game. And we see that in our that the output of our algorithm beats the opponent most of the time. So it significantly improves over the confounded baseline. So what we can also do is try to visualize which graph our policy inferred. So we do that in the following way. We take a certain frame from the simulator, here at NeurIPS again. And then what we do is we encode this with this VE encoding that we use to represent the state in disentangled variables. And then for every dimension that the graph says is a nuisance variable, we sample a new real number from the prior, and put this into the encoding and do this a couple of times. And what we then see for a learned graph is that by doing this, we want the nuisance information to vary, and this is exactly what happens, and the causal information to stay fixed, because we resampled the things that our graph thought was a nuisance variable. And here we see that exactly happening. We see that the digit, which is a nuisance variable, varies, while the causal variables, the pedals and the ball, stay fixed. In comparison, if we were to do this with a random graph, we would see that all aspects of the scene vary. So both the nuisance and the causal variables, indicating that the learned graph really managed to learn to remove causal information and keep, remove nuisance information and keep causal information fixed. So some open questions. Most of these methods suffer from curse of dimensionality. As these problems became larger, it became harder to find well-performing causal graphs. And how to scale this up to larger problems seems hard. We used up to 50 dimensions, but to represent a really complicated scene in real driving, we probably want a much richer latent space, on which these methods probably wouldn't work out of the box. Second open question is how the variational causal discovery didn't work very well for anything larger than a mountain car. So curious, so it's quite an open question how to scale that up. Furthermore, this variational causal discovery we used for a very simple set of causal hypotheses, basically which state variable is a cause to the action. But you can easily imagine more complicated problems where you have where your space of causal hypotheses can be any directed acyclic graph, and how to parameterize spaces of directed acyclic graphs is a difficult problem. Lastly, the problem that I'm actually most interested in is the problem of how do you go from a pixel space, a unstructured high-dimensional input space, to a space on which you have variables that you can reason causally about. What we did here was using this variational autoencoder, but this is quite arbitrary. First of all, like the objective of the variational autoencoder does not really align with what we want. We want to have meaningful causal variables, and the variational autoencoder wants to have latent variables that are independent, and these criteria do not align. Furthermore, VAE loss is invariant under just rotating the entire latent space, but rotating a set of meaningful causal variables does not result in a new set of meaningful causal variables. So another argument why this VAE approach is not very principled. So exploring more principled causal representations, how we can learn, which is it seems a very open and maybe this is the whole problem of unsupervised learning, but at least it seems an important sub-question here. So in conclusion, we show that causal confusion occurs quite naturally in imitation learning, that only minor modifications to the state bring about significant drop in reward, and also some GTA experiments that show that adding some more information that you would like to add, like history, can actually harm performance rather than help it. We analyzed this with graphical causal models, analyzed it analytically in some toy setting, and showed that it exists in some relevant benchmarks, in which we solved it by trying to use a small number of targeted interventions and queries to an expert or observing some rewards. So as a conclusion, I think imitation learners should think about these causal situations, and as a consequence, just arbitrarily adding extra information to the learner may actually harm performance rather than improve it. So